As a last-ditch effort, Grupp rushed an application to the hospital pharmacy requesting permission to use the new therapy off-label. The board granted its approval for the IL-6 blocking drug that evening, and Grupp injected Emily with a dose in the ICU. 2 days afterward, on her 7th birthday, Emily woke up. "Boom," Dr. June said, waving his hands in the air. "Boom," he repeated. "It just melted away." We did a bone marrow biopsy 23 days later, and she was in a complete remission. "I have never seen a patient that sick get better so quickly," Grupp told me. The deft management of Emily's condition and her startling recovery saved the field of cell therapy. Emily Whitehead remains in that deep remission to this day. No cancer is detectable in her marrow or her blood. She is considered cured. If Emily had died, June told me, it's likely that the whole trial would have been shut down. It would have set back cellular therapy perhaps a decade or even longer. During a pause in the sessions at the conference, Emily and I joined a tour of the medical campus led by Dr. Bruce Levine, one of Dr. June's colleagues. He is the founding director of the facility at Penn where T cells are modified, quality controlled, and manufactured, and was among the first to handle Emily's cells. The technicians here worked singly or in pairs, checking boxes, optimizing protocols, shuttling cells between incubators, sterilizing their hands. The facility may as well have doubled as a small monument to Emily. Photographs of her were plastered on the walls. Emily at 8 in pigtails, Emily at 10 holding a plaque, Emily at 12 with missing front teeth, smiling next to President Barack Obama. At a certain point during the tour, I watched the real Emily looking out the window at the hospital across the street. She could almost see into the corner ICU room where she had been confined for nearly a month. The rain came down in sheets, streaking the windows with droplets. I wondered how she felt, knowing that there were 3 versions of her in the hospital. The one here today, on a break from school, the one in the pictures who had lived and almost died in the ICU, and the one frozen in the Krusty the Clown freezer next door. "Do you remember coming into the hospital?" I asked. "No," she said, looking out into the rain. "I only remember leaving." As I watched the advance and retreat of Sam's illness and the remarkable recovery of Emily Whitehead, I knew that I was also observing the birth of a kind of medicine in which cells were being repurposed as tools to fight illness. Cellular engineering. But it was also the replay of a centuries-old story. We are built out of cellular units. Our vulnerabilities are built out of the vulnerabilities of cells. Our capacity to engineer or manipulate cells, immune cells in both Sam's and Emily's cases, has become the basis of a new kind of medicine, albeit a kind of medicine that is still in mid-birth. If we knew how to arm Sam's immune cells more effectively against his melanoma without unleashing the autoimmune attack, would he be alive today? Spiral notebook in hand, writing sports pieces for a magazine? 2 new humans, examples of cellular manipulation and re-engineering. Emily, for whom our understanding of the laws of T-cell biology were seemingly sufficient to hold a lethal disease at bay for more than a decade, and hopefully for her lifetime. Sam, for whom we still seem to be missing some critical insight of how to balance a T-cell's attack on cancer and an attack on the self. What will the future bring? Let me clarify. I use the phrase new human throughout the audiobook and in its title. I mean it in a very precise sense. I explicitly do not mean the new human found in sci-fi visions of the future, an AI-augmented, robotically enhanced, infrared-equipped, blue pill-swallowing creature who blissfully cohabitates the real and virtual worlds, Keanu Reeves in a black muumuu. Nor do I mean transhuman, endowed with augmented abilities and capacities that transcend the ones we currently possess. I mean a human rebuilt anew with modified cells who looks and feels mostly like you and me. A woman with crippling recalcitrant depression whose nerve cells, neurons, are being stimulated with electrodes. A young boy undergoing an experimental bone marrow transplant using gene-edited cells to cure sickle cell disease. A type 1 diabetic infused with his own stem cells that have been engineered to produce the hormone insulin to maintain a normal blood level of glucose, the body's fuel. An octogenarian who, following multiple heart attacks, is injected with a virus that will home to his liver and permanently lower artery-clogging cholesterol, thus reducing his risk of another cardiac event. I mean my father, implanted with neurons or a neuron-stimulating device that would have steadied his gait so that he might not have suffered the fall that led to his death. I find these new humans and the cellular technologies used to create them vastly more exciting than their imaginary sci-fi counterparts. We've altered these humans to alleviate suffering, using a science that had to be handcrafted and carved with unfathomable labor and love, and technologies so ingenious that they stretch credulity, such as fusing a cancer cell with an immune cell to produce an immortal cell to cure cancer, or extracting a T cell from a young girl's body, engineering it with a virus to weaponize it against leukemia, and then transfusing it back into her body. We will meet these new humans in virtually every chapter in this audiobook, and as we learn to rebuild bodies and parts with cells, we will meet them in the present and in the future, in cafes, supermarkets, train stations, and airports, in neighborhoods, and in our own families. We will find them among our cousins and grandparents, our parents and siblings, and perhaps in ourselves. In a little less than 2 centuries, from the late 1830s, when the scientists Matthias Schleiden and Theodor Schwann proposed that all animal and plant tissues were made of cells, to the spring of Emily's recovery, a radical concept swept through biology and medicine, touching virtually every aspect of the two sciences and altering both forever. Complex living organisms were assemblages of tiny, self-contained, self-regulating units, living compartments, if you will, or living atoms, as the Dutch microscopist Antony van Leeuwenhoek called them in 1676. Humans were ecosystems of these living units. We were pixelated assemblages, composites, our existence the result of a cooperative agglomeration. We were a sum of parts. The discovery of cells and the reframing of the human body as a cellular ecosystem also announced the birth of a new kind of medicine based on the therapeutic manipulations of cells. A hip fracture, cardiac arrest, immunodeficiency, Alzheimer's dementia, AIDS, pneumonia, lung cancer, kidney failure, arthritis, all could be reconceived as the results of cells, or systems of cells, functioning abnormally. And all could be perceived as loci of cellular therapies. The transformation of medicine made possible by our new understanding of cell biology can be broadly divided into 4 categories. The first is the use of drugs, chemical substances, or physical stimulation to alter the properties of cells, their interactions with one another, their intercommunication, and their behavior. Antibiotics against germs, chemotherapy and immunotherapy for cancer, and the stimulation of neurons with electrodes to modulate nerve cell circuits in the brain fall in this first category. The second is the transfer of cells from body to body, including back into our own bodies, exemplified by blood transfusions, bone marrow transplantation, and in vitro fertilization, IVF. The third is the use of cells to synthesize a substance, insulin or antibodies, that produces a therapeutic effect on an illness. And most recently, there is a fourth category, the genetic modification of cells, followed by transplantation to create cells, organs, and bodies endowed with new properties. Some of these therapies, such as antibiotics and blood transfusion, have been so deeply entrenched in the practice of medicine that we hardly think of them as cellular therapies, but they arose from our understanding of cell biology. Germ theory, as we shall soon see, is an extension of cell theory. Some other therapies, such as immunotherapy for cancer, are 21st century developments. Yet others, such as the infusion of modified stem cells for diabetes, are so new that they are still considered experimental. Yet all these, the old and the new, are cellular therapies because they depend critically on our understanding of cell biology. And each advance has changed the course of medicine and equally changed our conception of being human and living as humans. In 1922, a 14-year-old boy with type 1 diabetes was resuscitated from a coma, born anew, as it were, by the infusion of insulin extracted from the pancreatic cells of a dog. In 2010, when Emily Whitehead received her infusion of CAR, chimeric antigen receptor, T cells, or 12 years later, when the first patients with sickle cell anemia are surviving, disease-free, with gene-modified blood stem cells, we are transitioning from the century of the gene to a contiguous, overlapping century of the cell.
Your team has destroyed
A cell is the unit of life. But that begs a deeper question. What is life? It may be one of biology's metaphysical conundrums that we are still struggling to define the very thing that defines us. Life's definition cannot be captured by a single property. As the Ukrainian biologist Sergei Sokolov put it, every theory, hypothesis, or point of view adopts life's definitions in accordance with its own scientific interests and premises. There are hundreds of working conventional definitions of life within scientific discourse, but none has been able to achieve a consensus. And Sokolov, who unfortunately died in the prime of his intellectual life in 2009, would know, as it was the particular stone in his shoe. He was an astrobiologist. His research involved finding life beyond Earth. But how can one find life if scientists are struggling to define the term itself? Life's definition, as it stands now, is akin to a menu. It is not one thing, but a series of things, a set of behaviors. a series of processes, not a single property. To be living, an organism must have the capacity to reproduce, to grow, to metabolize, to adapt to stimuli, and to maintain its internal milieu. Complex, multicellular living beings also possess what I might call emergent properties, properties that emerge from systems of cells, such as mechanisms to defend themselves against injury and invasion, organs with specialized functions, physiologic systems of communication between organs, and even sentience and cognition. And it is not a coincidence that all these properties repose, ultimately, in the cells or systems of cells. In a sense, then, one might define life as having cells, and cells as having life. The recursive definition is not nonsensical. Had Sokolov met his first astrobiological being, say an ectoplasmic alien from Alpha Centauri, and asked whether she, he, it is living or not, he might have asked whether this being fulfills the menu of life's properties. But he might have also queried the being, "Do you have cells?" It is difficult to imagine life without cells, just as it is impossible to imagine cells having no life. Perhaps that fact outlines the importance of the story of the cell. We need to understand cells to understand the human body. We need them to understand medicine. But most essentially, we need the story of the cell to tell the story of life and of ourselves. What is a cell, anyway? In a narrow sense, a cell is an autonomous living unit that acts as a decoding machine for a gene. Genes provide instructions, code, if you will, to build proteins, the molecules that perform virtually all the work in a cell. Proteins enable biological reactions, coordinate signals within the cell, form its structural elements, and turn genes on and off to regulate a cell's identity, metabolism, growth, and death. They are the central functionaries in biology, the molecular machines that enable life. Genes provide the code to build ribonucleic acid, RNA, that in turn is deciphered to build proteins. But aside from carrying the code to make proteins, some of these RNAs carry out diverse tasks in cells, some of which are yet to be deciphered. RNA can also regulate genes and function in concert with proteins in some biological reactions. Genes, which carry the codes to build proteins, are physically located in a double-stranded, helical molecule called deoxyribonucleic acid, DNA, which is further packaged in human cells into skein-like structures called chromosomes. As far as we know, DNA is present inside every living cell. Scientists have hunted for cells that use molecules other than DNA to carry their instructions, RNA, for instance. But so far, they've never found an RNA instruction-carrying cell. By decoding, I mean that molecules within a cell read certain sections of the genetic code, like musicians in an orchestra reading their parts of a musical score, the cell's individual song, thereby enabling a gene's instructions to become physically manifest in the actual protein. Or, put more simply, a gene carries the code. A cell deciphers that code. A cell thus transforms information into form, genetic code into proteins. A gene without a cell is lifeless, an instruction manual stored inside an inert molecule, a musical score without a musician, a lonely library with no one to read the books within it. A cell brings materiality and physicality to a set of genes. A cell enlivens genes. But a cell is not merely a gene-decoding machine. Having unpacked the code by synthesizing a select set of proteins that is encoded in its genes, a cell becomes an integrating machine. A cell uses this set of proteins and the biochemical products made by proteins in conjunction with one another to start coordinating its function, its behavior, movement, metabolism, signaling, delivering nutrients to other cells, surveying for foreign objects, to achieve the properties of life. And that behavior, in turn, manifests as the behavior of the organism. The metabolism of an organism reposes in the metabolism of the cell. The reproduction of an organism reposes in the reproduction of a cell. The repair, survival, and death of an organism repose in the repair, survival, and death of cells. The behavior of an organ or an organism reposes in the behavior of a cell. The life of an organism reposes in the life of a cell. And finally, a cell is a dividing machine. Molecules within the cell, proteins again, initiate the process of duplicating the genome. The internal organization of the cell changes. Chromosomes, where the genetic material of a cell is physically located, divide. Cell division is what drives growth, repair, regeneration, and ultimately reproduction among the fundamental defining features of life.
Victory!
I have spent a lifetime with cells. Every time I see a cell under a microscope, refulgent, glimmering, alive, I relive the thrill of seeing my first cell. On a Friday afternoon in the fall of 1993, about a week after I had arrived as a graduate student in Alan Townsend's lab at the University of Oxford to study immunology, I had ground up a mouse spleen and plated the blood-tinged soup in a petri dish with factors to stimulate T cells. The weekend passed, and on Monday morning I switched on the microscope. The room was so dimly lit that it was not even necessary to pull down the curtains. The city of Oxford was always dimly lit. If cloudless Italy was a land made for telescopes, then foggy dark England seemed custom-made for microscopes, and I put the plate under the scope. Waiting beneath the tissue culture medium were masses of translucent, kidney-shaped T cells that possessed what I can describe only as an inner glow and a luminous fullness, the signs of healthy, active cells. When cells die, the glow dims, and they shrivel and turn granular, or pycnotic, to use the jargon of cell biology. Like eyes looking back at me, I whispered to myself, and then, to my astonishment, the T cell moved, deliberately, purposefully, seeking out an infected cell that it might purge and kill. It was alive. Years later, then, it was nothing less than thrilling, mesmerizing, to watch the cellular revolution unfold in humans. When I first met Emily Whitehead in a fluorescent-lit corridor outside the auditorium at the University of Pennsylvania, it was as if she had allowed me to enter a portal that linked the future and the past. I trained as an immunologist at first, then a stem cell scientist, and finally a cancer biologist, before I became a medical oncologist. I even had a brief foray into neurobiology between 1996 and 1999, when I worked with Professor Connie Sepko at Harvard Medical School, studying the development of the retina. I studied glial cells long before they were in vogue in neurobiology. Sepko, a developmental biologist and geneticist, taught me the science and art of lineage tracing, a method that we will encounter later in this audiobook. Emily embodied all these past lives, not just mine, but, more importantly, the lives and labors of thousands of researchers, looking down thousands of microscopes over thousands of days and nights. She embodied our desire to get to the luminous heart of the cell, to understand its endlessly captivating mysteries. And she embodied our aching aspiration to witness the birth of a new kind of medicine, cellular therapies based on our deciphering the physiology of cells. To encounter my friend Sam in his hospital room and watch his remission and relapse whiplash him week upon week was to experience an opposite chill, not exhilaration, but an apprehension of how much there was yet to learn and know. As an oncologist, I focus on cells that have gone rogue, cells that have marauded spaces where they should not exist, cells dividing out of control. These cells distort and overturn the very behaviors that I describe in this book. I try to understand why and how that happens. You might think of me as a cell biologist caught in an upside-down world, and so the story of the cell is one that is stitched into the very fabric of my scientific and personal lives. As I wrote furiously from the early months of 2020 into 2022, the COVID-19 pandemic continued wildfiring its way throughout the globe. My hospital, my adopted city of New York, and my homeland overflowed with the bodies of the sick and the dead. By February 2020, the ICU beds at Columbia University Medical Center, where I work, were full of patients drowning in their own secretions, with mechanical ventilators forcing air in and out of their lungs. The early spring of 20 was particularly bleak. New York turned into an unrecognizable, wind-blown metropolis of empty byways and avenues, where people hid from people. India's most lethal surge hit almost a year later in April and May 2021. Bodies were burned in parking lots, back alleyways, slums, and children's playgrounds. At the crematoria, the fires burned so often and so briskly that the metal grids holding the bodies corroded and melted. I sat in a clinic room in the hospital at first, and then, when the cancer clinic itself was pared to its bare minimum, isolated with my family at home. Staring out the window at the horizon, I thought yet again about cells, immunity, and its discontents. The Yale University virologist, Akiko Iwasaki, told me that the central pathology caused by SARS-CoV-2, severe acute respiratory syndrome coronavirus 2, was immunological misfiring, a dysregulation of immune cells. I had not even heard the term before, but its immensity hit me. At its core, the pandemic, too, was a disease of cells. Yes, there was the virus, but viruses are inert, lifeless without cells. Our cells had awoken the plague and brought it to life. To understand crucial features of the pandemic, we would need to understand not just the idiosyncrasies of the virus, but also the biology of immune cells and their discontents. For a while then, it seemed as if every byway and avenue of my thinking and being led me back to cells. I'm not sure how much I conjured this book into life, and how much this book demanded to be written. In The Emperor of All Maladies, I wrote about the aching quest to find cures for cancer or to prevent it. The gene was propelled by the quest to decode and decipher the code of life. The Song of the Cell takes us on a very different journey, to understand life in terms of its simplest unit, the cell. This book is not about hunting for a cure or deciphering a code. There is no single adversary. Its protagonists want to understand life by understanding a cell's anatomy, physiology, behavior, and its interactions with surrounding cells, a cell's music. And their medical quest is to seek cellular therapies, to use the building blocks of humans to rebuild and repair humans. Rather than a chronological unfolding, then, I had to choose a very different structure. Each part of the book takes a fundamental property of complex living beings and explores its story. Each part is a mini-history, a chronology of discovery. Each part illuminates a fundamental property of life, reproduction, autonomy, metabolism, that reposes in a particular system of cells, and each contains the birth of new cellular technology, say bone marrow transplantation, in vitro fertilization, IVF, gene therapy, deep brain stimulation, immunotherapy, that arises from our understanding of cells and challenges our conceptions of how humans are built and how we function. The book is itself a sum of parts, history and personal history, physiology and pathology, past and future, and an intimate chronicle of my own growth as a cell biologist and doctor, spun together into a whole. The organization is cellular, if you will. When I began this project in the winter of 2019, I chose initially to dedicate it to Rudolf Virchow. I was taken by this reclusive, progressive, soft-spoken German physician-scientist who, resisting the pathological social forces of his times, promoted free thinking, was a champion of public health, despised racism, published his own journal, carved a unique and self-assured path through medicine, and launched an understanding of the study of diseases and organs and tissues based on dysfunctions of cells, cellular pathology, as he described it. I returned, in the end, to a patient, a friend, being treated for cancer with a novel form of immunotherapy, and Emily Whitehead, patients who had opened new inroads into our understanding of cells and cellular therapy. They were among the first to experience our early attempts to harness cells for human therapy and to transform cellular pathology into cellular medicine, partially successful and partially not. It is to them and their cells that this book is dedicated. Part 1. Discovery. Both of us, you and I, began as single cells. Our genes are different, albeit marginally. The way our bodies develop are different. Our skin, our hair, our bones, our brains are all built differently. Our life experiences vary widely. I lost 2 uncles to mental illness. I lost a father to a deadly spiral following a fall, a knee to arthritis, a friend, so many friends, to cancer. And yet, despite all the yawning gaps between our bodies and experiences, you and I share 2 features. First, we arose from a single-celled embryo, and second, from that cell came multiple cells, those that populate your body and mine. We are built of the same material units and are akin to 2 different nuggets of matter built from the same atoms. What are we made of? Some ancients believed that we were created by menstrual blood that had congealed into bodies. Some believed we came preformed, mini beings that just expanded over time, like human-shaped balloons blown up for a parade. Some thought humans were sculpted from mud and river water. Some thought we transformed gradually in the womb from tadpole-like beings to fish-mouthed creatures and finally into humans. But if you look down a microscope at your skin and mine, or your liver and mine, you would find them strikingly alike, and you'd realize that all of us were, in fact, built out of living units, cells. The first cell gave rise to more cells, and then divided to form even more, until our livers and guts and brains, all the elaborate anatomical architectures in the body, were gradually formed. When did we realize that humans were, in fact, composites of independent living units, or that these units are the basis of all the functions that the body is capable of? In other words, that our physiology reposes, ultimately, in cellular physiology? And conversely, when did we posit that our medical fates and futures were intimately linked to the changes in these living units, that our diseases are consequences of cellular pathology? It is to these questions, and embedded within them the story of a discovery that touched and radically transformed biology, medicine, and our conception of humans, that we first turn. The original cell, an invisible world. True knowledge is to be aware of one's ignorance. Rudolf Virchow, letter to his father, circa 1830s. Let us give thanks first to the softness of Rudolf Virchow's voice. Virchow was born in Pomerania, Prussia, now split between Poland and Germany, on October 13, 1821. His father, Karl, was a farmer and a city treasurer. We know little of his mother, Johanna Virchow, née Hesse. Rudolf was a diligent and bright student, thoughtful, attentive, and clever with languages. He learned German, French, Arabic, and Latin, and earned distinctions for his academic work. At the age of 18, he wrote his high school thesis, "A life full of work and toil is not a burden but a benediction," and began to prepare for a professional life in the clergy. He sought to become a pastor and preach to a congregation, but Virchow was anxious about the weakness of his voice. Faith emanated from the strength of inspiration, and inspiration from the strength of elocution. But what if no one could even hear him as he tried to project from the pulpit? Medicine and science seemed like more forgiving professions for a reclusive, studious, soft-spoken boy. Upon graduation in 1839, Virchow received a military scholarship and chose to study medicine at the Friedrich Wilhelms Institute in Berlin. The world of medicine that Virchow entered in the mid-1800s might have been divided into two halves, anatomy and pathology. One relatively advanced and the other still in a muddle, respectively. In the 16th century, anatomists began to describe the forms and structures of the human body with increasing precision. The best-known anatomist of all was the Flemish scientist Andreas Vesalius, a professor at Padua University in Italy. The son of an apothecary, Vesalius arrived in Paris in 1533 to study and practice surgery. He found surgical anatomy in absolute disarray. There were few textbooks and no systematic map of the human body. Most surgeons and their students depended loosely on the anatomical teachings of Galen, the Roman physician who lived between AD 129 and 216. Galen's centuries-old treatises on human anatomy were based on animal studies, had become badly outdated, and frankly, were often incorrect. The basement of Paris's hospital, Hôtel Dieu, where decaying human cadavers were dissected, was a dingy, airless, badly lit space with half-feral dogs roaming underneath the gurneys to gnaw on the drippings. A meat market, as Vesalius would describe one such anatomical chamber. The professors sat on lofty chairs and cackled like jackdaws, he wrote, while their assistants hacked and tugged through the body at random, eviscerating organs and parts as if pulling out cotton stuffing from a toy. The doctors did not even attempt cutting, Vesalius wrote bitterly, but those barbers, to whom the craft of surgery was delegated, were too unlearned to understand the writings of the professors of dissection. They merely chop up the things which are to be shown on the instructions of the physician, who, having never put his hand to cutting, simply steers the boat from the commentary, and not without arrogance. And thus all things are taught wrongly, and days go by in silly disputations. Fewer facts are placed before the spectators in that tumult than a butcher could teach a doctor in his meat market. He concluded grimly, aside from the 8 muscles of the abdomen, badly mangled and in the wrong order, no one had ever shown a muscle to me, nor any bone, much less the succession of nerves, veins, and arteries. Frustrated and confused, Vesalius decided to create his own map of the human body. He raided charnel houses near the hospital, sometimes twice a day, to haul specimens back to his laboratory. The graves at the Cemetery of the Innocents, often open to the air, with bodies ground to the bone, provided perfectly preserved specimens for skeletal drawings. And walking by Montfaucon, the massive 3-tiered gibbet of Paris, Vesalius spotted prisoners' corpses hanging from the gallows. He would secretly make off with the freshly hung bodies, their muscles, viscera, and nerves intact enough for him to flay them open layer by layer and map the locations of the organs. The intricate drawings that Vesalius produced over the next decade transformed human anatomy. Occasionally, he cut the brain into horizontal sections, like a melon sliced down from its tip, to create the kind of images that a modern computerized axial tomography, CAT scan, might produce. Other times, he overlaid the blood vessels above the muscles or opened the muscles into flaps, like a series of anatomical windows that one could imagine passing through to reveal the surfaces and layers beneath them. He might draw the human abdomen visualized from the bottom up, like the 15th century Italian painter Andrea Mantegna's perspective of Christ's body in the Lamentation of Christ, and cut the picture into slices, in the way that a magnetic resonance imaging, MRI scan, might visualize it. He collaborated with the painter and printmaker Jan van Kalkar to produce the most detailed and delicate drawings of human anatomy that existed. In 1543, he published his anatomical works in 7 volumes entitled De Humani Corporis Fabrica, the fabric of the human body. The word fabric in the title was a clue to its texture and purpose. This was the human body treated like physical material, not mystery, made of fabric, not spirit. It was part medical textbook with nearly 700 illustrations and part scientific treatise with maps and diagrams that would lay the foundation for human anatomical studies for centuries to come. A sample can be seen in the attached PDF. Coincidentally, it was published the same year that the Polish astronomer Nicholas Copernicus would put out his Anatomy of the Heavens, the monumental book The Revolutions, on the revolutions of heavenly spheres, which featured a map of the heliocentric solar system that placed the Earth in orbit and the Sun firmly at its center. Vesalius had put human anatomy at the center of medicine. But while anatomy, the study of structural elements of the human body, made radical advances, pathology, the study of human diseases and their causes, had no such center. It was a mapless, dispersed universe. There was no comparable book of pathology and no common theory to explain diseases, neither revelations nor revolutions. During the 16th and 17th centuries, most diseases were attributed to miasmas, poisonous vapors emanating from sewage or contaminated air. The miasmas carried particles of decaying matter called miasmata that somehow entered the body and forced it to decay. A disease such as malaria still carries that history, its name created by joining the Italian mala and aria to form bad air. Early health reformers thus concentrated on sanitary reform and public hygiene to prevent and cure illness. They dug sewage systems to dispense waste, or opened ventilation ducts in homes and factories to prevent the contagious fog of miasmata from accumulating indoors. The theory seemed to be fogged by an indisputable logic. Many cities, undergoing rapid industrialization and unable to deal with the influx of wage workers and their families, were malodorous arenas of smog and sewage, and disease seemed to track the worst-smelling, most populated areas. Resurgent waves of cholera and typhus stalked the poorer parts of London and its vicinities, such as the East End, now glistening with shops and restaurants selling high-end linen aprons and expensive bottles of single distillery gin. Syphilis and tuberculosis were rampant. Childbirth was a terrifying event, with a distinct likelihood of ending not in birth but in death, of the infant, the mother, or both. In the wealthier parts of town, where the air was clean and sewage adequately discarded, health prevailed, while the poor, who lived in miasma-filled areas, inevitably succumbed to illness. If cleanliness was the secret to health, then disease must be a condition of uncleanliness or contamination. But while the notion of vaporous contamination and miasmata seemed to carry a vague ring of truth, and provided perfect justification to further segregate rich and poor neighborhoods and cities, the understanding of pathology was riddled with peculiar puzzles. Why, for instance, did a woman who gave birth in one part of an obstetrics clinic in Vienna, Austria, have nearly 3 times the rate of postpartum death compared with a woman who gave birth in the adjacent clinic? What caused infertility? Why would a perfectly healthy young man suddenly succumb to a disease that racked his joints with the most excruciating pain? Throughout the 18th and 19th centuries, doctors and scientists searched for a systematic way to explain human diseases. But the best they could achieve was an unsatisfactory surplus of explanations that ultimately relied on gross anatomy. Each disease was the dysfunction of an individual organ: the liver, the stomach, the spleen. Was there some deeper organizing principle that connected these organs and their diffuse and mystifying disorders? Could one even think of human pathology in a systematic manner? Perhaps the answer was not to be found in visible anatomy, but rather in microscopic anatomy. Indeed,
Welcome to Summoner's Rift. Seconds until minions spawn. Minions have spawned. Has been slain. An enemy has been slain. An ally has been slain. been slain. An enemy has been slain. Your team has destroyed a turret. Shut down. has destroyed a turret. Triple kill! An ally has been slain. An ally has been slain. Your team has destroyed a turret. Shut down. has been slain. Enemy double kill. An ally has been slain. Your team has destroyed a turret. Slain. An enemy has been slain. Your team has destroyed a turret. An ally has been slain. Your team has destroyed an inhibitor. Enemy rampage. You have slain an enemy.